Welcome back, students. In the last lecture, we derived a series of integrated rate laws that we use to describe elementary kinetic steps. Real chemical reactions have mechanisms that are built upon multiple elementary steps. Today, we will investigate some more realistic reaction mechanisms that are applicable to many reactions. In the next couple of lectures after this, we're going to look at more complex reaction mechanisms involving many steps. The learning goals for today are going to be to explain some important approximations. And these are the steady state approximation and the rate limiting step approximations that simplify greatly the rate law expressions. We'll get some information into the origins of the rate constant using the Arrhenius equation to see how the temperature affects the rate constant. And we'll see some rate laws for various chemical reactions. We're not going to go too far into the math today. All of the math is essentially the same as we did in the last class, except for it's a little bit more complicated. So the strategy is always set up the rate laws, see how the concentrations of all the reactants, intermediates, and products change with respect to time, make appropriate assumptions, and then integrate to find the integrated rate law. We'll start with a sequential first order reaction. So in this reaction, we have reactant A being consumed at a rate of Ka and making I, and then I is consumed at a rate with Ki to make product. So we have reactant into intermediate into product, and these are all first order reactions. How can we describe the rate law for this process? Well, we can come up with the following rate law. We can say that the change in A with respect to time is equal to negative Ka times the concentration of A, because A is consumed based only on the concentration of A and the rate constant Ka. However, I is produced based on A and Ka and consumed based on I and Ki. So we have this production and consumption of I. P is only produced based on I and K sub I. So we can construct these rate expressions and integrate to find the appropriate rate laws. It turns out that this A, this first one here, this is the exact same equation that we've already solved in the last class. So we can solve this expression and get that A is equal to the initial concentration of A times e to the minus Ka t at an exponential to K. The other solutions follow from this. They're a little bit more math involved in doing so. To solve for the concentration of I as a function of time, we make the substitution once we know what the concentration of A as a function of time is, and then there's a standard integral we can use to solve that, and we get this expression here. And then we can plug this in for P. We know that the concentration of product is equal to the initial concentration of A minus all that is still A and all that is still I, and putting all that together, we get this expression here. These equations look scary, but we can conceptualize them quite easily. So our first equation says that A is consumed in an exponential decay, as all that happens to A is it makes the intermediate. I, on the other hand, is actually produced by A, but then I is consumed to make P. So what must happen to I is that I initially increases, but then eventually exponentially decreases to make P. And that is what this scary math is saying. Now for P, we know that P is produced by I in an exponential decay fashion, eventually increasing to 1. However, A must be first converted into I, and so there's a lag. And so all of this nonsense over here introduces a lag for P. So it should look something like this. Now we can actually go to a Desmos plot to observe these as a function of time and of changing the rates. So here we can see a scenario like we saw on the board. But what happens if we change these things? So if Ka is much larger than Ki, conceptually, what does that mean? That means the rate of A being converted to I is faster than I being converted to P. So if Ka is much larger, what we should observe, and what we do observe mathematically, is a large amount of I. So we see a lot of I being produced. And this is what happens if our Ka is much greater than Ki. What if we have the other way around? Well, if Ki is greater, that means the rate of I going to P is faster than A going to I. So we should not actually get very much I involved. So if Ki is much greater than Ka, what we see is something like this, where we have a very low population of I ever being formed, and it more or less looks like A is going directly into P. We do still see a little bit of a lag there, but that lag can decrease if we change the ratios here. We can introduce some assumptions to help us with the math here. So I have the exact same plot that I had before, although I have changed the bounds here. So now our KIs and our KAs can go to 100. So here, this is the situation where KI is much faster than KA. So we have a very small amount of KI, or of I ever being formed. So we can go about this mathematically, but we can also assume a rate limiting approximation. And in this rate limiting step approximation, what matters is actually the slowest step. So if Ki is faster than Ka, Ka is going to be the limiting step here. And so what we can do is plot something only based on Ka. And that's actually what's shown here in the red. So this is our rate limiting step assumption, and here's the actual data if we don't assume that, and you can see that they're pretty accurate. Now, in the assumption that Ki is not much greater than Ka, they actually start to get pretty far off. So if we change this down, now you can see that the assumption stops being very good. And if we switch it, right, then it's totally different. So if Ki is low and Ka is high, then this assumption is bad. But now we need to switch to the other assumption, that is Ki is the rate limiting step. So instead of making Ka the rate limiting step, we make Ki the rate limiting step. We can see that again, that gives us a pretty good approximation of the way that the product is formed without considering the intermediate. So this is known as the rate limiting step approximation. We can go back to the slides here. We can see some more plots of this. This rate limiting approximation, again, is pretty good in the limit when one rate is significantly faster than the other, or the others if we have a more complex mechanism. And this is, again, is very useful for simplifying very complex reactions, and it's a pretty good assumption if one of your rates is very slow compared to the others. Another approximation that's very helpful but is not quite as good is known as the steady state approximation. So in this example, there's two intermediates. Now, mathematically, we can solve this equation, and it's pretty hard to do. And I'm not going to go through the math of how we can solve this equation, but imagine reaction with two intermediates, and you could think of, right, enzymatic pathways in biology that have many more than two intermediates. So this is a real example. It's much easier to assume a steady state approximation, which is that the concentration of intermediate species does not change. Now, in a reaction mechanism, this is obviously bad, right? Because we start with pure A and we end up with P. We obviously have to make and consume both intermediates. But if we look at how this predicts the reaction, it's reasonable. So it has the same slope basically at every point. It is shifted because we definitely missed the lag phase in the production of these intermediates. But it makes the math so much simpler. So if we use the steady state approximation, we say that the rate of the intermediates are not changing as a function of time. And this allows us to basically say that I1 is a bunch of rate constants, right, times A naught, and then I2 is the same. And at the end of the day, our product is only based on the initial concentration of A and the rate of converting A into essentially P. We're ignoring the intermediates. Again, this is appropriate only when the rate for A to either the intermediates is the slowest one. And we can see again that we have not a large amount of intermediates produced. If that's not true, this is very bad and it's not an appropriate assumption to use. Now, we're going to use the steady state approximation quite frequently throughout the next couple of lectures because it's very useful for us in simplifying otherwise complex rates. Another aspect that's important to include in real chemical reactions is parallel reactions. Chemical reactions often produce side products that are undesirable. Go back to your organic chemistry experience to verify this. It turns out that the rates at which potential products are formed determine how much of each product is formed. So consider the reaction here. We have an initial starting compound A that could go to product B or side product C, depending on the rates KB and KC. Just like before, we can set up rate laws determining how A, B, and C change with time. So A is consumed based on Kb in the concentration of A, but also Kc in the concentration of A. And we can pull these together to see that dA dt is equal to negative Kb plus Kc times the concentration of A. Now, A doesn't know which rate, how it's being consumed, right? So we can add Kb plus Kc, those are just rate constants, to get an effective rate constant. So this essentially has not changed our rate law for A. B is formed based on Kb times the concentration of A, and C is formed based on Kc times the concentration of A. We can solve this just like we've done in the past to find that the concentration of A is equal to the initial concentration times E raised to the sum of the rate constants times T. However, when we evaluate B and C, we find that B is equal to, again, we see this A naught 1 minus E to the minus Kb plus Kct. But we have this out here, Kb over Kb plus Kc. This is effectively a normalization constant that tells us how much B we get. So the amount of B we get is simply the rate constant of B over the sum of the total rate constants. And the same is true for C. So in this reaction here, the rate constant of forming B is twice as much as C. And so we get 2/3 B and 1/3 C. And we could show this mathematically. We can also define a percent yield, which is exactly what we've done here. If there's more than 2 products that we can form, we simply say the percent yield is equal to the rate of forming whatever product we're interested in, divided by the sum of all of the products. Now that we've pretty well defined how the concentration of reactants affects the rate, let's look a little bit more into the rate constant that also affects the rate. So the reaction takes place when the molecules collide, in the case of bimolecular reactions, in the proper orientation with enough energy to overcome the activation barrier. Collisions are based on the concentration of molecules, which you've already figured out how those affect the rates, but they're also based on the diffusion rate of the molecules. Another factor to consider is proper collisional orientation, which depends on the reactants. The more complex the reactants are, the more the orientation will matter. But it's typically on the order of 1 in 10,000 collisions is actually in the proper orientation for the reaction to occur. The last thing to consider, and that's what we're going to consider here, is the activation energy. Consider a gas molecule. How likely is a gas molecule to have enough energy to overcome the activation barrier? Now, what had been noted in the late 1800s by Arrhenius is that there's a relationship between the rate constant and temperature. And he noted specifically that the rate constant, the natural log of the rate constant, appears to be a function, a linear function of 1 over the temperature. And he put this together into the Arrhenius rate law, which is that K is equal to a pre-exponential factor that depends on things like diffusion coefficient, collisional frequency, and so forth. A times e to the minus activation energy over RT. So the more energy we give a molecule, the higher the temperature, the more likely it is to overcome the activation barrier. Now, this is exactly what we would expect based on our kinetic theory of gas model. If we have a situation like this where the reactants need to overcome a certain activation energy to make products, the higher the temperature, the more likely we are to have molecules at high speeds. Molecules at high speeds have more energy, and so we're more likely to actually overcome this activation barrier. And that's where this expression comes from. It comes from the kinetic theory of gas, essentially converting mv squared over kt into an energy over RT. And that's where this expression comes from. This simple relationship is not always followed. It assumes that the pre-exponential factor, which is the capital A here, and the activation energy are not functions of temperature. We'll see some more modern theories of kinetics at the end that kind of try to connect the two to maybe more general reactions. However, there are many reactions for which this expression is appropriate. When we write out the reaction in this way, we can see that if reactants have to overcome an activation barrier to make products, then products also have to overcome an activation barrier to make reactants. And we're familiar with this as chemists. Most reactions are reversible. So we can describe a reversible reaction where A goes to B and B goes to A, and there's different rate constants. And these constants are going to be different because there's different activation barriers that these must overcome. We're comfortable with this from thermodynamics, saying whichever one has the lowest energy is the one that's going to be dominant at equilibrium. We can actually describe this process of reversible reactions with our rate laws. So again, we can construct equations where we have dA dt. A is consumed based on a unimolecular reaction with Ka, and B is produced based on a unimolecular reaction with B. And then B is produced by A and consumed by B. So we have these reactions here. We can investigate equilibrium by solving this. So we can say that the initial concentration, if we only have A, if the initial concentration of A is equal to A plus B, we plug this in to get a solution for this. Again, we're not going to go through the math too much here, but we end up with these funky equations. So we have the initial concentration of A, resume in 3. So we have the concentration of A being equal to the initial concentration of A, and then plus this complex expression here, and we have a similar thing for B. What happens to these at infinite time? In other words, what happens at equilibrium? Well, at equilibrium, T is infinity, and so this e to the minus to the negative infinity is equal to 0. So the concentration of A simply becomes A naught times Kb over Ka plus Kb. And the concentration of B becomes, and it's a little bit hard to see from this math here, but it becomes Ka over Ka plus Kb. And so what that means is the equilibrium concentrations of A and B depend only on the relative rates of forming B and forming A. So the equilibrium concentration of B is equal to the initial concentration of our material A, the only thing we have at the beginning, times the rate at which B is formed, divided by the sum of how B is formed and produced. And the same is true for A. So what we end up getting then is an expression that looks like this. We have an exponential decrease in A. There's an apparent rate constant for A, that's the sum of Ka plus Kb. And then we end up with a non-zero concentration of A and a non-1 concentration of B at infinite time. Once the concentration stops changing, we have reached equilibrium. And we can define the equilibrium constant based on, of course, the concentration of B over A, like we've done in thermodynamics. But we can also base it on the rate. It's also equal to the rate of Ka over Kb. So this result here connects thermodynamics, equilibrium, with rates. We can have an expression for the equilibrium constant based on the equilibrium concentrations, thermodynamics, but also based on the rates, which is kinetics. So we can relate thermodynamics and kinetics here with this notion of equilibrium. If we actually want to solve for these values, we can do it pretty easily. We can't get it just from the rate or the equilibrium alone, but this rate is the sum of Ka plus Kb, and then the equilibrium concentrations give us the ratio of Ka and Kb. So we have a systems of equations that we can solve. We can also look at diffusion-controlled reactions like we've done in Lab 5. We can imagine a reaction where A and B collide to make a collision complex AB, and then they can either dissociate with a reverse rate or form product based on a product forming rate. Using the steady state approximation, we can come up with an expression that's the rate of this reaction is equal to Kp, the rate of forming product, times the concentration of AB. The concentration of AB doesn't change with time under the steady state approximation, so we can end up with this expression here. We can consider this in two limits. If the rate of forming product is much greater than the rate of dissociating without forming product, Kr, then Kp plus Kr is essentially just Kp. And this reaction boils down to Kd times the concentration of A and B. In other words, like we saw in lab 5, this reaction is governed strictly by diffusion. It doesn't matter what Kr and Kp are, as long as Kp is much greater than Kr. If we assume our reactants are spherical, which is often done, we can actually get an expression for what Kd might be based on the radius of the molecules, as shown here using the Stokes-Einstein equation for the diffusion coefficient. In the other limit, if Kr is much greater than Kp, this reaction is more complicated and depends on the rates of all three rate constants here. I also want to briefly introduce two additional concepts before we finish the lecture. The first one I'll introduce is potential energy surfaces, and then I'll talk about activated complex theory. Potential energy surfaces represent three-dimensional pathways to convert between reactants, and you can see some examples here. In thermodynamics, we often say that it doesn't matter which path a reaction takes, as long as we go from reactants to products, since they're all state functions. However, we can appreciate that reactions will take specific paths. Just like you or I would, they're going to take the path of least resistance. These potential energy surfaces can be constructed based on experimental data, as is shown here. However, it's often more useful to just have them as, concepts or conceptual tools to imagine difficult processes. And the one that I'm most familiar with is something like protein folding. So these are very similar to a reaction coordinate that we might draw where we have reactants going to products. You can attempt to draw three-dimensional surfaces for them. You can also just draw things like protein folding funnels, and maybe you've seen that in your biochemistry class. So I wanted to make you aware that these tools exist, and we can use them to try to chart how A and B might go to B and C. The last thing I'll mention is activated complex theory. So activated complex theory is an attempt to bring in statistical thermodynamics into these rate equations. This is developed to provide a theoretical basis for kinetics. The ideas behind activated complex theory are that as you go from A and B, so AB plus C to A plus BC, there's some sort of transition state that we have to encounter. You can think of this, right, as like a 5-bonded carbon. You've done these sorts of things in organic chemistry. So there's some sort of activated complex theory transition state that we might encounter. So consider the reaction here where we have A plus B goes to an AB transition state, and it can either go back to A and B or it can make product. Very similar to what we just did for diffusion controlled reactions. What we're going to do in this case is assume that equilibrium is established between A plus B and AB. And so the assumption here is that K1 and K minus 1 are much faster than K2, such that we reach an equilibrium before we make K2. Now, when we do this, we can define the concentration of this transition state intermediate based on the equilibrium constant. And then we have to divide by a standard concentration to keep our units balanced. And then we have A and B. Now, why do we do this? Well, in doing this, what this allows us to do, if we have an equilibrium constant between, again, it's just the equilibrium between A plus B and AB. So you can appreciate this here. The equilibrium constant is equal to AB over A plus B. So obviously this is true. If we have Kc is equal to AB over A plus B, we can sub that in here, and these two are equal to each other. So with this, we can define the rate as the change in product with respect to time, which is simply equal to K2 times the concentration of our intermediate, which is then equal to this here. Now we get into some shenanigans. So what's going on here is we're saying that K2 is equal to kappa, where kappa is a constant that talks about how likely we are to actually form products, and nu. Now, what our nu is a frequency at which the bond stretches. So we have some bond, in this case, the A, maybe we're breaking a bond in A and making our product B. In this case up here, we're breaking the AB bond and making BC. But we have some weak bond that we're probably breaking in a chemical reaction. And so nu is the frequency at which this bond stretches. What we do next, again, this is going to look complicated. I'm not going to test you on this. This is just so you can know that there is theory that goes into these things. We break down the equilibrium constant based on its partition function like we described before. And what we do is we pull out the partition function for the vibrational degree of freedom that's being broken. So what we can say is that our equilibrium constant is equal to QRC. This is the reaction coordinate partition function, the very weak bond that we're breaking. We'll say that this is equal to KBT over H nu, where KB is Boltzmann's constant to differentiate it from all the other Ks we have going on here. T is the temperature, and then H nu, H is Planck's constant, nu is the frequency at which that vibrates. We're doing this because we're assuming that the bond is weak, and therefore the weak bond is able to essentially be continuous. It has a low energy, otherwise it wouldn't be broken. And with this, we can get an interesting expression for the rate constant K based on first principles. We can go back and compare this to the Arrhenius rate law. I'm not going to go into this in too much detail, but essentially what we do is we can end up saying that here we have K is equal to kappa KBT over HC times the equilibrium constant. We can break that equilibrium constant down through the free energy into entropy and enthalpy, and that gives us this expression here. So our activated complex theory predicts that K is equal to Boltzmann's constant times the temperature over H times this normalization C. And then we have E raised to the delta S of the transition state, the entropy change of the transition state compared to the reactants over the gas constant times E to the minus delta H of the transition state over RT. And so putting this together, comparing this with the Arrhenius rate law, we can kind of get an estimation for what these are. Now, the actual applications are different. And so you can see some of these here, depending on if you have solutions or a gas phase. So for a bimolecular collision in solution, we end up with this expression here, where we have our pre-exponential factor is equal to E, and that comes from this guy here. We have E KBT over HC naught times E to the delta S of the transition state over R. Again, not temperature independent, so we can see there's a temperature dependence here. And then the activation energy is simply equal to delta H plus RT, the energy that's required to overcome the activation barrier. And again, I'm not going to go into this in too much detail, but just to show you that modern theory is a little bit more accurate than the Arrhenius rate law, but still bears a lot of resemblance to the Arrhenius rate law. To conclude our basics of equilibrium here, the thermodynamics that we can use determines whether reactants or products will be present in equilibrium, but we need this kinetics, this reaction mechanisms to actually occur how a reaction occurs with time or in terms of the mechanism of that reaction. We can actually use pretty simple kinetics to understand a variety of real chemical reactions. We'll see in the next lecture how we can extend this to more complex reactions. The integrated rate laws are used to fit experimental data to determine order. Remember, the reaction order cannot be predicted based on the stoichiometric reaction, but must be experimentally measured. We'll see some more weird examples of this next time. And then the rate constant is based on things like activation energy, diffusion, and collisions.